Today, we're diving into something pretty amazing, a potential breakthrough in creating fresh water called Diesel pie. And what's so wild about it is where the inspiration comes from. One of the most sophisticated, most efficient filters we know of. And that question right there is really the whole point. What if, instead of trying to invent some brand new, complicated machine from scratch, we could just, well, copy a system that's been perfected over millions of years of evolution, a system that's running inside every single one of us right now. So let's talk about the problem we're actually trying to solve. Right now, to make 1 cubic meter of fresh water from the ocean, and that's 1,000 liters, it costs between 3 and 4 kilowatt hours of energy. That number, that's the fundamental challenge. That's the high price we're paying for every single drop. Yeah, that energy cost is the main thing we're up against with today's standard method, which is called seawater reverse osmosis, or SWRO. But honestly, it's not the only problem. These huge plants also struggle with their membranes getting clogged up. It's a massive issue called fouling. And then there's the environmental headache of what to do with all that super salty wastewater, the brine that gets left behind. But what if the clue for a better way has been hiding in plain sight, in a really unexpected place? The mammalian kidney. Your kidneys, right now, are quietly, efficiently conserving water with mind-boggling precision, and there's no power plant attached. Turns out, nature has already solved this puzzle.
So how on earth does it work? What is the kidney's secret sauce? Understanding this little biological marvel is the absolute key to unlocking the whole Desal pie concept. It really is a beautiful piece of natural engineering.
Okay, so the kidney's core trick is something called the counter-current multiplier. Now stay with me here. Imagine two tiny tubes running right next to each other, but the liquid inside is flowing in opposite directions. In one tube, water gets pulled out into an environment that's getting saltier and saltier. And in the other tube, salt is actively being pumped out to create that very saltiness. This whole loop creates this incredibly powerful gradient that just yanks water out with very little energy. And this brings us to the really brilliant part. The goal here isn't to, grow a kidney in a lab. It's to translate the logic of how it works, that flow system, into an engineered device. And here's exactly how they map that biology onto a piece of tech. This slide just lays it out perfectly. So the part of the kidney that lets water out, that becomes a hollow fiber lined with these amazing things called aquaporin proteins. They're basically nature's perfect water channels. The part that pumps the salt out, that's replaced by a low-voltage electrodialysis channel, which just uses a gentle electric field to nudge salt ions away. And the secret to making that countercurrent thing happen, you have to get those two channels incredibly, incredibly close together. So let's look at the chip itself. Seawater flows into the first channel. This one uses something called forward osmosis. The easiest way to think about it is just natural water movement. Water is naturally drawn across a membrane from a less salty place to a more salty one. And this channel is lined with those aquaporin proteins. They're like perfect little bouncers at a club door that only let water molecules through. Salt can't get in. Okay, now running right alongside it, but in the opposite direction, is the electrodialysis channel. Remember how the water was drawn into a saltier solution? Well, this is that solution. As it flows along, a tiny electric field gently pushes the salt ions out of it. This basically recharges the solution, making it salty again so it's ready to pull even more fresh water across from the other channel. It's a continuous loop. And here's the kicker. None of that multiplier magic, none of it, works unless these two channels are practically touching. The whole design hinges on a gap of less than 100 micrometers. We're talking about the width of a human hair. That tiny, tiny space is what allows the saltiness in one channel to directly power the water movement in the other, perfectly mimicking the kidney's incredible efficiency. Okay, so this all sounds amazing in theory, right? But of course, an idea this revolutionary is going to face some massive engineering hurdles. Let's be real, this is not easy to build. But what's so cool here is that the designers have actually thought about these hard problems and come up with some equally clever solutions. First up, those amazing aquaporin proteins. Well, they're notoriously fragile. You put them in real-world seawater, they can break down or get clogged up super fast. The proposed solution is pretty slick. Protect them with a nanoscopically thin second skin made of graphene oxide. It gives the delicate biological machinery a tough, durable coat of armor. The next huge headache is keeping that tiny 100 micrometer gap perfect. How do you stop tiny leaks between the channels, especially when you've got an electric field running right there?
The answer is a specially designed buffer foam, a material that's both a flexible seal and an electrical insulator. It basically absorbs vibration and stops any cross-contamination in its tracks.
So, if they can solve all those challenges, what's the prize? This is the payoff. The design is targeting an energy use of 2.0 kilowatt hours per cubic meter, or even less. Now, when you compare that to the 3 to 4 kilowatt hours of current systems, that is a gigantic leap in efficiency. It's a total game changer. All right, so we've gone from the biology of a kidney all the way down to the engineering of a single microchip. But how do you go from one tiny chip to a system that can actually provide a meaningful amount of water for people? The answer, as it so often is in modern engineering, is modularity. The vision here is to bundle these chips together into a bigger cartridge, which they're calling a kidney rack. And a single one of these racks is designed to produce about 10 cubic meters, that's 10,000 liters, of fresh water every single day. That's enough for a small community or a local neighborhood. And this isn't just some dumb box. It's designed to be really, really smart. Each cartridge has isolation valves, which means you can hot swap it for maintenance without shutting the whole system down. It's got built-in sensors that act like little smoke alarms to detect any leaks instantly. And get this, each unit even gets a health score, which allows for predictive maintenance before a failure ever happens. And really, this quote from the team just nails the entire philosophy. It's not about building one single, gigantic billion-dollar plant. It's about perfecting a small, efficient module and then scaling up just by adding more of them. It's about thinking small to go big. You know, the Desal concept is such a powerful reminder that some of the best ideas out there aren't waiting to be invented. They're just waiting to be discovered in the world around us and sometimes even inside us. It really makes you wonder, doesn't it? What other elegant solutions has nature already perfected, just waiting for us to pay attention and translate them?